All right, 7.3 part 1, starting on page 166 of your notes packet. Our first objective is to solve systems of equations by converting between an augmented matrix and a system of equations, and to perform elementary row operations, find row echelon form for a matrix. So what does all that mean? Well, when we're working with matrix, we can use these operations called Gaussian eliminations. So there are 3 different types of operations or moves that we can make in order to use Gaussian elimination. And this is going to help us solve a system of equations by using matrices. So let me see if I can get into focus here. That's a little bit better. Okay, so the first move that we can make is to interchange any 2 equations. Interchange any 2 equations of the system. And what this does is it's really just really writing the equations in a different order. So leaving the equations the same, but reordering which one goes first and which one goes second, for example. The second thing we can do is we can multiply or divide, which is the same as multiplying by a fraction, one of the equations by any non-zero real number. So this would be like multiplying an equation by 2, so distributing that to every term, including both sides of the equal sign, or multiplying by a half or something like that to one equation. And then our third option is kind of a combination of the second and adding the 2 equations. So it's adding a multiple of one equation to any other of the other equations in the system. Now our goal for using Gaussian elimination is to reduce our system of equations into row echelon form. So what is row echelon form? Well, it's a matrix with the following conditions. The rows consist entirely of zeros occur at the bottom. Rows consisting entirely of zeros, if any, occur at the bottom of the matrix. Okay. Also, the first entry in any row with non-zero entries is 1. So you can have leading zeros followed by a 1 and then other numbers, but the first non-zero number is a 1. And lastly, the column subscript of the leading 1 entries increases as the row subscript increases. So what does that mean? That means the ones are forming a downward diagonal, almost like with a negative slope. So an example would be something like 1, 3, 4, 8, 0, 1, 7, 0, 0, 0, 0, 0. Okay, so all the row with all the zeros is at the bottom, and our first non-zero number in any row is a 1, and the ones are kind of decreasing. The subscript is increasing of the column and the row. In order to put it into reduced row echelon form, we would also add the condition that every column that has a leading one has zeros elsewhere. So an example of reduced row echelon form, and it's not the same as the example above, would be 1, 0, 0, 0, 5, 0, 1, 0, 0, 2, 0, 0, 1, 0, 8, something like this. So we have our ones still going in a diagonal, but everything else except for the last column is zeros. All right, let's take a look at actually using this. Okay, so in example 1, we want to solve this given system of equations. So we're going to go ahead and put it into a matrix. Now remember, the matrix is using just the coefficient of each term. So our matrix will have 1, and then -2, 1, 7, 3, -5, 1, 14, 2, -2, -1, 3. And we would call this row 1, row 2, and row 3. Okay, now already the first cell in row 1 is a leading 1. So that row is already in kind of echelon form. Okay, so what I want to do next is try to put rows 2 and 3 also into row echelon form. So what action I'm going to take is I'm going to take row 2 minus 3 times row 1. Now this is option 3 for our Gaussian elimination steps. And when I do this, all I'm changing is row 2. So row 1 stays the same, and row 3 stays the same. And the first cell of row 2 is going to be 3 minus 3 times 1. So I have 0. And then -5 minus 3 times -2. So that's -5 plus 6 gives me 1. And then 1 minus 3 times 1 gives me -2. And 14 minus 3 times 7 leaves me -7. Okay, this is my new modified matrix. The next operation I'm going to do, I'm going to write it up here, but I'll do the operation down here. So row 3 minus 2 times row 1. So again, rows 1 and 2 are now staying the same, and row 3 is the only thing that's changing. So 1, -2, 1, 7, 0, 1, -2, -7. Row 3 minus 2 times row 1. So 2 minus 2 is 0. 2 now minus -2 times -2. So -2 minus -4 is 2. -1 minus 2 is -3. And 3 minus 14 is -11. Now, I still need to get a 0 now in the second slot, so I'm going to do row 3 minus 2 times row 2. So rows 1 and 2 still staying the same. 1, -2, 1, 7, 0, 1, -2, -7. 0 minus 0 is 0. 2 minus 2 times 1, so that's 0. Negative 3 minus 2 times negative 2, so negative 3 plus 4 is 1. And negative 11 plus 14 is 3. Okay, so now I am in row echelon form, but I want to keep going, okay? And I want to get reduced row echelon form. So the next action that I'm going to take, I'm going to, let's do row 2 plus 2 times row 3. Okay, so my goal now is to get a 0 in the second row. Okay, so I'm not changing rows 1 or 3. 1, negative 2, 1, 7, and 0, 0, 1, 3. I'm only changing the second row. So 0 and 0 gives me 0. 1 and 0 gives me 1. Negative 2 plus 2 gives me 0. Negative 7 plus 6 gives me negative 1. All right. Oh, I'm off screen. I'm sorry. There we go. So the second row is now 0, 1, 0, negative 1. Now my third and second rows are in reduced row echelon form, but I need to fix my first row. Okay, so I will start by using rows 1 and 2 so that I can get a 0 where that negative 2 is. So we'll say row 1 plus 2 times row 2. So now it's rows 2 and 3 that are staying the same. 0, 1, 0, negative 1, 0, 0, 1, 3. And row 1 is changing. 1 plus 0 is 1. Negative 2 plus 2 is 0. 1 plus 0 is 1. 7 minus 2 is 5. And then hopefully this will be our last move, getting a 0 in this cell that has a 1. So I'm going to use row 1 and row 3. And I'm going to do row 1 minus row 3, or row 1 plus negative row 3. So again, rows 2 and 3 are staying the same. 0, 1, 0, negative 1. 0, 0, 1, 3. And only row 1 is changing. So 1 plus 0 is 1, or 1 minus 0. 0 minus 0 is 0. 1 minus 1 is 0. 5 minus 3 is 2. So notice, if you look just at the square matrix at the front of our resulting matrix, it looks like an identity matrix. If we were to cover up the last column, that looks like an identity matrix, okay? So we could say that this is like the I3 matrix, and what this tells us is that x equals 2, y equals negative 1, and z equals 3. So we end up with the ordered triple 2, negative 1, 3. All right. Using these same steps, go ahead and try examples 2 and 3, and then we'll also go over how to do this on your calculator. All right, so just like we've done previously, in order to make our matrix, you go into second, and then above the inverse button is matrix. Okay, and then we're going to edit, and enter our matrix. So I have a 3 by 4 matrix, 3 rows, 4 columns, 3 by 4. Okay, and then I'm going to put in my numbers. 1, negative 2, 1, 7, and then 3, negative 5, 1, and 14, and 2, negative 2, 1, and 3. Okay, so now my matrix matches my matrix that I like to solve. And then quit. Now when we go back into the matrix menu, we'd like to use the matrix to do a calculation. In order to put the matrix into reduced form, we're going to come down all the way to our ref. Say enter. What do we want to use? We want to use matrix A, our 3x4 matrix. Okay, so all of those were in the matrix menu. Second, above the inverses matrix. Now it will give it to me in reduced form, in reduced row echelon form. So notice all of our row operations ended with our reduced reference matrix. So on your calculator, you want to use ref of your matrix. And I'm just going to label it as matrix A. It could be matrix B or matrix C, but in our example, I use matrix A. Okay, and you interpret this reference matrix the same way as you interpret the reduced row echelon matrix. This would be your first variable. 1 times your first variable equals 2. 1 times your second variable equals -1. 1 times your third variable equals 3. So x is 2, y is -1, and z is 3. All right, looking past examples 2 and 3 that you finished on your own, we're looking at invertible square linear systems. So let A be the coefficient matrix of a system of n linear equations in n variables given by A times x equals B, where x is the n by 1 matrix of variables and B is the n by 1 matrix of numbers on the right-hand side of the equations. If A inverse exists, then the systems of equations has the unique solution x equals A inverse times B. Okay, so what this means is we have our matrix of coefficients times our matrix of variables equals our matrix of solutions. Then our matrix of variables equals the matrix of coefficients inverse times the matrix of solutions. All right, now let's apply that. So A is our coefficients. So that would be 3, -3, 6, 1, -3, 10, -1, 3, -5. X is our variables. So that's x, y, z. And B is our solutions, which is 20, 40, 30. All right, using what we just talked about on the last page, we can say that the determinant of A, and remember you can find this on your calculator, is -30, which is not 0. Okay, in order to find the inverse, the determinant cannot be 0. So that means that we can use A times x equals B and find that x equals A inverse times B. So now we need to find our A inverse matrix. So A inverse equals, again, you can find this on your calculator. All right, so our inverse matrix is 1/2, -1/10, 2/5, and I've already checked that there's no additional digits. That ... just signifies the closing brackets. 1/6, 3/10, 4/5, 0, 1/5, 1/5. All right, so then I can use our new matrix along with matrix multiplication to find that x equals 1/2 times -1, or 1/2, -1/10, 2/5, 1/6, 3/10, 4/5, 0, 1/5, 1/5 times 20, 40, 30, which gives us a resulting matrix of 18, 39.3 repeating, 14. So our result is that our first variable is 18, second variable is 39.3 repeating, and our third variable is 14. So we have the ordered triple 18, 39.3 repeating, 14. If you need reminders on how to do those steps on the calculator, you can go back to our previous notes videos for a refresher. Lastly, think about what you've done in this lesson and summarize what you learned from this video and in class.